Let's take a look at solving systems of quadratic equations. So a system of quadratic equations is two or more quadratic equations, and in this case we're going to also look at a combination of quadratic and linear. And the solutions are points where they intersect or points that they have in common. So we're going to use solving by substitution, and we're going to have solving for y if they're not already equal to y to help us out, set them equal to one another, and then solve for x by factoring, set them equal to 0, and then find y by substituting the solutions into, and that's supposed to be a parentheses, into one of the original equations. And you can substitute back into either one of the original equations, but we'll look at that with the examples. And note that you may have more than one solution at the end. So when you look at a graph of a system of quadratic and linear equations, there are three possibilities. They could not touch at all and have no solution. They could touch one time and have one solution, or they could touch twice and have two solutions or 2 points that they have in common. So that is a graphic example of a quadratic and linear system. These are systems of quadratic equations. So if you have two quadratic equations, they could touch twice and you have two solutions. They could touch one time, so you have one solution or 1 point they have in common. And of course, they could not touch at all, and you would have no solution. So these are the two types of systems that we're going to look at. Now we're going to solve them algebraically, but we could graph it and take a look at the solution on a graph to check our answer. So let's just look at how to solve this using solving by factoring. So for example 1, we're given y equals x squared plus 3x plus 9 and y equals negative 3x plus 4. So the first equation is quadratic. We know because it has a squared as its highest exponent. And the second one is linear because it does not have a square. It only has x as its highest variable or exponent or power. So we're going to set these equal. They're already equal to y, so if they're both equal to y, we're allowed to say that they would equal each other. So x squared plus 3x plus 9 is equal to negative 3x plus 4. And now, like we've done in the past, we need to put everything on one side. So we need to add the 3x. And we can go ahead and subtract the 4. So that way we're moving everything over to the left. So then we end up with x squared plus 6x plus 5, all on the left-hand side, equal to 0. So it's in standard form. And then let's use our t-bar, because it's a trinomial, to see if we can find factors. So we need to find factors that will multiply to give us 5x squared and add up to 6x. So 1x times 5x will add up to 6x. And also multiply to give us 5x squared. So remember, we use these numbers to replace our middle term. So I'm going to write that as 1x plus 5x, which is equal to 6x. Bring down the first term and the last term. It's still equal to 0. Then we're going to use grouping, just like we've done before. And we're going to factor out the greatest common factor of the first group. So that would be x. And then we have x plus 1 left over. And then in the second group, we can take out a 5, and we have x plus 1 left over. So we're just solving by factoring. So then let's put together the GCFs. So x plus 5 goes together. And one of our matching factors of x plus 1 is our factor. So then we need to set those equal to 0 because we're solving by factoring. So we got to keep going a little further and say x plus 5 equals 0 and x plus 1 equals 0. And so if we subtract 5, we get x equals negative 5. And if we subtract 1, we get x equals negative 1. Now we need to think of what a system of equations means. It means that this is two graphs. And we can tell by our solution so far that we have 2 points where they're going to touch, but we only have x values. So it's kind of like this example. They touch twice, but we need to figure out what would be the y coordinate of those points, because remember, points have an x and a y coordinate, and we only have x's so far, so we need to plug those back into one of the original equations. Now, if you look at those two equations, which one looks easier to plug this back into? Certainly this one looks a little easier to plug things back into. So let's say y equals, and take this first x value and plug it in. So y equals -3 times -5 plus 4, which will be 15 plus 4, which is 19. So one of our solutions is -5, 19. Now we're finished with that one. And now I'm just going to grab a different color to keep things separated. X equals -1, we have to do the same thing. So use that same linear equation just because it's easier to plug it into. And we have -3 times -1 plus 4. So I'm just taking it and plugging it into this original equation that looks easier. And then we simplify. So y would equal 3 plus 4, which is 7. So our other solution is -1, 7. So that means that these are 2 points on our graph where this quadratic and linear equation would intersect and have those points in common. So just because I don't want you to confuse all of these circles, the last two that I circled, I'm even going to erase this again, just so you see the circled part right there at the very bottom in purple and orange. Those are our 2 points that are solutions. All right, let's look at one more example. Let's see. So we are given 2 quadratic equations. Both of these are quadratic. We can tell because they have a squared x in the front as our ax squared term, our quadratic term. So we're going to set them equal to each other because they're both equal to y. We can set them equal to each other. All right, so then we need to get everything on one side. So I'm going to move all 3 of these over here to the left. So by moving them, I need to add the x squared, do the opposite operation. I need to subtract 3x and subtract 7 to get everything on one side. So then I end up with 2x squared, because there's like a 1 in front of each of those. 9x minus 3x would be 6x, and then 7 minus 7 would cancel out. Alright, so now we're going to solve by factoring again. So this one is not a trinomial, so I can just take out a greatest common factor of 2x. Then I would have x plus 3 left over. And now I'm already done factoring. I can set them both equal to 0. So 2x equals 0, x plus 3 equals 0, and then solve for x. So divide both sides by 2. My pen messed up a little bit. So then I get x equals 0, and then subtract 3. I get x equals -3. But you have to be careful because you feel like you're finished at that point, but you're not finished yet because remember, these are 2 values where the graph is going to touch. But that means they are ordered pairs. We have the x, but we need to figure out the y. So you have to go back and plug these into whatever looks easiest from your original equations and find the y values that they go with. So let's take a look up here. Now I would say out of these 2, seeing as how this one has a negative sign, I would pick the first one to use to plug it back in, but it doesn't matter which one you use. So just so you can see it, I'm going to write it down again and then scroll back down to my x values that I'm going to plug in. So I'm going to plug in x equals 0, so 0 squared plus 9 times 0 plus 7. So 0 plus 0 plus 7 means that 7 is my y value that goes with 0. Then I'm going to plug in negative 3 for the other one. So negative 3 squared plus 9 times negative 3 plus 7. So that would be 9 minus 27 plus 7. So 9 minus 27 is negative 18 plus 7 gives me negative 11. Alright, so those are the 2 points where these two quadratic equations would intersect if we